No, I see. Here's my share screen. Sorry, I'm having a problem with my computer. This one. Hi guys. I have a problem with my Zoom, so please be patient today. I hope that I think Zoom decided to update this morning, and now it's like acting weird and really slow. So I hope things are going to work okay. So please be patient today. Okay. All right, does everybody, can you guys all see me and hear me? People who are here? Can people, let's see, give me a second, I'll be able to see. You can hear and you can see okay? It's really glitching out over here too. Hopefully, if things go weird, then I may have to like stop the lecture and then restart the meeting, but I'll let you know if it comes to that. Hopefully it won't come to that, but I will let you know if it does. Let's see, Zoom's acting really weird. Let me put this in. Okay. I love technology. All right. Let me do this. Make sure everybody here. My picture, my window here is like glitching like that. So that will settle down too as we go along. Okay, waiting for people to join. Okay, so today we're going to finish up chapter 3.3. Okay, we started that yesterday, and then we're going to move on to chapter 3.4. Okay, it looks like we'll be able to finish up 3.3 and 3.4 today, work through the examples and go through all of that. We can talk about it if you guys want to vote. We can vote on it if you want. I was intending to have the exam only cover up to chapter 3.4, and then we could leave tomorrow as like a review class if you guys want to come with questions on the homework, on the test reviews that I've been putting up. I've also actually started putting up homework solutions online too. So I put it's in a subfolder under the homework directory. There's a subfolder called homework solutions, and I put up the solution sets for 2.2, 2.3, and 2.4 so far, so that you guys can take a look. I know I've graded for completion on your homeworks, and so you want to be able to take a look to see if you actually did the homeworks correctly. So take a look at the solution set. I'll start posting things more tonight and tomorrow so that you can see, you know, what you need to have in order to be successful in the exam. Let me think about that. Yeah, so, and then we can, you know, at the end of class, if you guys want to include 3.5 in the exam, or if you put that off until next week, I'm totally fine with that. If we put it off till next week, then 3.5 will be on next week's quiz, and the exam will only cover up to chapter 3.4. That's fine. If we decide not to include 3.5, there are things on that review sheet that don't make any sense to you, right? Because they're not going to be included. So we'll talk about that at the end of class. I'll tell you what things, what it looks like, so that you know you can know whether or not it's something that's actually not included or something that you're just not recognizing. Okay, so with that said, let's go ahead and finish up with chapter 3.3. So let me make sure this is here in the screen. Okay, so chapter 3.3, we were talking about discrete random variables. Make sure she's in. Okay, so discrete random variables. Make sure this is all in focus here. Okay, and that should focus. Good. That looked better before. How about that? You know, I'm having technology problems here today. Okay, so discrete random variables. So what we want to actually do with these, we're going to finish this up. So discrete random variables are things just like you would think discrete means, right? That I have only a very finite number of options. You know, it's funny, it focuses really well at first and then it goes out of focus. That's horrible. Don't know if it's doing that. I'm sorry, I'm trying to get this camera to work so that you guys can actually see what I'm writing. And it's not working here. See if we can get it to force it out of focus. Try that one again. Doing it and then it goes out. Okay, I'm just going to stop there. All right, so discrete random variables. So we have a finite set of options that we can choose from. And we also talked the other day, yesterday, about building up a probability density or probability mass function for our discrete random variables. And when we did that, let's see, was it yeah, on our example page, right? So we had, this was our probability density function on the last example that we chose. These were the outcomes that we could have, okay? These were the individual probabilities on that outcome. Okay, and if I summed up all of these rectangles here, right, if I took the area under my curve, essentially, this whole thing's gonna sum up to 1. Okay, that's how we actually know that we're dealing with a valid probability density or probability mass function, okay, is that all the probabilities sum up to 1. And all of the individual probabilities are between 0 and 1. Okay, and then from here, I can look along my PDF and I can say, okay, so the probability that my random variable is equal to 5 is gonna be, I'm just gonna go across here, okay? Or the probability that my random variable is gonna equal to 7, go over to here, find it on my graph, and I go over and I find out what the probability is, okay? I can do this for multiple and then add them up like we did in the earlier example, okay? So this is our probability density function. It's a way of graphically looking at our table, which we did yesterday, right? So we had these different possibilities. So this was example 4 that we did yesterday. We have 2 die, we're gonna sum up their bases, basically graph out what their probability distribution is, right? Or what the sums could possibly be, okay? So we came up with that, we graphed it out, and then we took a look at it. So there's a concept on here that I want to be able to finish off on our probability distributions, and it's called a cumulative distribution function. So let's write that down, and we'll talk about what it is, and then we'll actually calculate it for this last example. So a cumulative so what we call a CDF, a cumulative distribution function. Cumulative distribution function is like a rolling sum, okay? So it's a rolling sum as I go along. Okay, so when I look at my probability distribution function, I can go right along and find the outcome and then find along the y-axis what its probability is. But for every point along my cumulative distribution function, I'm summing up all of those probabilities that have happened before. Okay, so we'll talk about why these things are important as we go along. It's something that we're going to be using when we think about statistics and probabilities. Okay, so let me write down our definition for our CDF, and then we'll do an example. Okay, the last example, we'll do a CDF for that last example. So a cumulative distribution function is a function that gives the probability that the random variable, and it could be whatever we call it, but we've been calling it x, is less than or equal to some value k. Okay, so unlike our PDF where we say this is the probability that our random variable is equal to this value, our cumulative distribution function says when I get to this point, that's the probability, the value here on my y-axis is the probability that my random variable is less than or equal to this value. So we're accumulating all of those probabilities as we go, okay? So what this means is we're gonna sum up all the probabilities for x, our random variable, being less than or equal to k, okay? Maybe it doesn't quite make sense, but we're actually gonna build one based on the previous example that we just did. Okay. So I'm gonna get out my, this is still chapter 3.3, so I'm looking at the next page, okay, which is example 5, okay, on 3.3. So given the previous example, what's our cumulative distribution function? So this is still taking, I've got die 1, die 2, okay? I'm gonna throw these die, I get, 1 through 6 possibilities of an output. I've got 1 through 6 possibilities. I'm gonna sum up the base values on these, right? So I have a certain set of values, right? 2 through 12 as sums, right? And each of these sums has a different probability. That's what we've been plotting, okay? So for this, we're actually gonna do our cumulative distribution function, okay? So let's think about it. This says we're gonna sum up as we go along. So the first thing I'm gonna do is I'm gonna think about, let's remember our sums. So our sums from before, we said I could have a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, right? I've got 2 die faces, I'm summing them up. These are the possible values for the sums that I could get, okay? So the probability that my random variable x, big X, okay, is less than or equal to 2. Okay, now for this, I'm going to that table. That table that we made on the previous example, okay? So I'm looking here on this table here, right? So the probability that x is less than or equal to 2, well, all we have is our lowest value is that x is equal to 2. So 1 out of 36, okay, is the probability that x is less than or equal to, sorry, is less than or equal to 2. Okay, so it's 1 out of 36. Now, when I say the probability that x is less than or equal to 3, I'm going to go through my whole sum values. I'm going to take what I had before, my probability that x is less than or equal to 2, and I'm going to add in when x is less than or equal to, when x is equal to 3. So I'm going to start accruing, and I'm going to start summing up everything that we go. So when x is equal to 3, we had 2 out of 36 possibilities. So this gave us 3 out of 36. I'm just going to leave things in terms of 36 for now, just so I can have common denominators to add things up. So the same thing for x is less than or equal to 4. So 4 means, right, I'm going to add in my 2. I'm going to add in my 3. And I'm going to add in the probability that x is equal to 4. That came from what we had before. So that's 3 out of 36. Okay. And then this was going to equal to 6 out of 36. And that's 4. We're accumulating probability. So again, for 5, x is less than or equal to 5. Okay. So now what I'm going to do is I'm going to take this 6 out of 36 because it's everything that I've summed up before. Okay. And then I'm going to add in probability that x is equal to 5. That was equal to 4 out of 36. Okay. So this is 10 out of 36. So this 6 right here, right there, and this 6 is our sum from when x is equal to 2, when x is equal to 3, when x is equal to 4. That's contained in this 6 value right there. This 4 comes from when x is equal to 5. Okay, so I'm summing it up. Same thing when x is less than or equal to 6. I take what I've summed up already, so 10 out of 36, and I add in 5 out of 36. This 5 out of 36 comes from when x is equal to 6. This 10 comes from here. Okay, that's our previous sum. Okay. Probability that x is less than or equal to 7. Okay, I'm going to add in my 15, 36 plus what 7 is equal to. 7 was 6 out of 36. Okay, so this one was 21 out of 36. Okay, see how we're adding in all these sums. So this, I'll just keep marking this where these numbers are coming from. So 8, I'm going to take my sum already, my previous sum, 21 out of 36, and I'm going to add in when x is equal to 8. So x was equal to 8, I got 5 out of 36. I'm looking at my table. So 26 out of 36. Now probability when x is less than or equal to 9, right? I'm going to take my previous sum, I'm going to add in when x is equal to 9. Okay, so this here comes from there. Okay, so I'm summing up. I'm accumulating all these sums. Probability that x is less than or equal to 10. See, that's why we don't say probability that x is equal to 10. That would be our probability mass function. Okay, probability that x is less than or equal to 10. That says, you know, I'm starting at 10. When 10 and all the other possible values below that point, okay, that's what this sum is telling me here. Cumulative distribution function is very helpful for a number of things. So I'm going to take this 30 out of 36. And now I'm going to add in my 10. I'm looking at my table 3 out of 36. And then 11. X is less than or equal to 11. I take my previous sum and I add in, so this is my previous sum, I'm going to add in my values. This is 2 out of 36, 35 out of 36, and then my 12. X is less than or equal to 12, right? So my previous sum, 35 out of 36, comes from here, plus our probability that x is equal to 12, which I can't talk and write at the same time, right? This is 36 out of 36, which is equal to 1. At the end of our cumulative distribution function, we should have summed up all those probabilities along the way. We're getting to our max, which is equal to 1. Okay, our whole point about our cumulative distribution function is to start at our minimum. Sometimes it's 0, sometimes it's a value. It's going to depend on the nature of the function. And then it's going to max out at 1 because I've accumulated all of those probabilities as we go. Okay, so my last value is 1. It's also a good cross-check. Like, did you do all these probabilities right? So now we want to come up with a plot for a cumulative distribution function. Okay, so let's see. Running out of space here. So this plot's going to look like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and I'll do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so 1, 2, 3, 4, 6. So here's about roughly 0.5. Okay, and then this should be 1. Okay, so now this is our possible outcome. Okay, and this is the sum of our probabilities. This is just write sum of probabilities. This is a 1. Kind of wrote over the top of it. Okay, so in terms of our x-axis, our possible outcome, this is we're accumulating probabilities as we go. Okay, so I'm going to start. So for 2, our very first one. So 2 said it's going to be 1 out of 36. It's somewhere like right around here. I'm going to just start marking these out. 2, 3, 4. Right here. 5, 2, 3. Coming up with an approximate curve here. 6, 7, 8. So roughly right about there. 11, and then 12. So by the time I get, see if I can, I'll try to make these dark here. So this is the discrete function. I'll try to make this really evident. These are dots. I may have missed one. Okay, these are dots. It's a discrete function, right? So typically it should be a discrete graph, okay, and it should be smoother. I'm not drawing this out very well. Should be smoother, right? It's gonna basically start at our minimum value, and it's gonna max out at 1 at the top, okay? Now, right, we usually draw this. I'm gonna draw a very faint line. We connect the dots on here, even though this is a discrete function, because we like to see, aesthetically speaking, these sort of a smooth graph so we could read it more easily. Also, what would happen too in the real world is, even though this is a discrete outcome, you know, it's a very specific discrete outcome because we have dice values, you know, face values on our die. But sometimes what we can do is we can make the intervals between our discrete values really small so that we can get a better sampling value. Okay, so we can get a pretty smooth curve for what's happening. I think also aesthetically, we tend to like to look at graphs that are smoother, even though this is technically a discrete curve and it should just be dot. Okay, so how do we look at this, right? I state now, my probability that my outcome, my random variable, is less than or equal to 5 is this value here. That's 10 out of 36, okay? My probability that my outcome is equal to something, 12 or less, okay, is going to be equal to 1. I'm going to get something, right? So that's our probability here. Okay, so we're accumulating probabilities as we go, which is different than the probability mass function that we did yesterday, okay, which basically told us very specifically, depending on the outcome that we have, right, and the outcome that we have in its associated probability. Now, I've taken a running sum and I've added up these as I've gone to get this graph right here, our probability, our cumulative probability distribution function right there, okay. This is an important concept. We're going to use this a lot when we get into statistical analysis, because we're going to be looking at probabilities, and we're going to look at values, potentially for values of probability. We're looking for values where like some random variable is going to be either between these values, or it's going to be less than or equal to this value, or greater than or equal to this value. So we need to have other ways of being able to conceptualize it. Okay, so that was finishing up example 5, doing a cumulative distribution function for the rolling of the 2 dice. Okay, actually wanted to work through a problem from the back of the book, chapter 3.3.10. I think it's similar to some of the problems that you're working on for homework, and I think it'd be really helpful to think about how we actually do it. So example 6, oops, let me get this out right here. Example 6 is actually a problem specifically from the textbook, okay, 3.3.10. We'll read it out, and then we're just going to work it through, okay. How we'll do out our sample size with the trees, sample space with the trees. We'll talk about our individual probability distribution functions, and then our overall probability distribution function as well. And then we can start putting it together. Let's see. Yeah, and then we can build up a CDF for it too at the end. Okay, so let's start at the beginning. So it says we've got earn 1 and earn 2. There's like buckets, right? And they each have 2 red chips and 2 white chips. So we're going to take 2 chips simultaneously from each earn. I'm going to take 2 chips here, 2 chips here, okay? And then I'm going to take a look. So then x1 is going to be our random variable for the number of red chips in the first sample from earn 1. x2 is going to be the random variable that gets assigned for the number of red chips in our second bucket, our second earn. So what we want to find is the probability distribution function for the sum of these 2, okay? Now, what we're going to also build up is we're going to do a PDF, a probability mass function too, for x1, and a probability mass function for x2 individually, just so we can see. And then we're going to use those to help us build up an overall probability distribution function for our sum. Okay, this is just so you can kind of see where everything is coming from. So let's first take a step back, back to kind of how we did it beginning, where we actually draw a picture out where we look at stuff. So I've got my first bucket here. This is number 1. So I've got 2 red and 2 white. And then I've got my second bucket, where I have 2 red and 2 white. Okay, so we're going to draw out our sample space just to see what it looks like, right? So I'm taking out 2 chips. We'll write it down. So we're going to take 2 chips or simultaneously. I'm taking out 2. Give me just a second. There. Okay, so I'm going to take out 2 chips from each earn. Okay, so what that means is if I take out 2 chips, I could get a red chip or a white chip. Okay, so the probability of getting red chips, right, is going to be, getting a red chip is going to be a 2 out of 4, because I have 2 red chips and 4 total. And here's 4 total. Okay, let's do out our tree here for the first one, and we'll do the tree out for the second one. So the first chip is red, okay? My first chip is red. My second chip could be red, okay? My second chip is going to be red. I have 1 red chip out of 3, right? In terms of my probability, okay? Because I've taken 1 out. Or I could have a white chip here, which would be, sorry, I'm running out of space here. 2 out of 3. Okay. Right, so this is going to give me that probability. Now for my white chip, say I've taken the first white chip out, I could get a probability of getting a white chip out is 2 out of 4, okay? Or on my second chip could be a red chip, which would be a 2 out of 3 probability. Or I could get a white chip, which would be a 1 out of 3 probability. So I get 1 red chip, 2 out of 4, another red chip, I've got 1 out of 3, okay? 1 red chip, 1 white chip, 1 white chip, 1 red chip, 1 white, 1 white. Okay, so let's kind of think about what these probabilities are. So this is the probability that my random variable x1 has 2 red chips, red, red, okay? That's going to equal to our multiplication of these probabilities along this path, 2/4 times 1/3. Okay, so I'm just going to write this out as 2/12. I'm going to leave it as 12 for now. We'll simplify it later. Okay, so now here, right, I'm going to multiply this here. So this is the probability that my random variable x1 is equal to 1 red chip, right? Because I have 1 red chip, 1 white chip. So you multiply our probabilities along this path, 2/4 times 2/3. Okay, so 2/4 times 2/3, this is 4/12. Okay, that's this path right here. Right here, I have 1 white chip, 1 red chip. So this is the probability that our random variable x1 is equal to 1 red chip. That was our random variable. They said how many red chips do we have? So x1. Okay, so x1 equals 1. I'm going to multiply the probabilities along this path. So I went white and then red. So 2/4 from here, and then 2/3 from here, okay, which is 4/12. And then here, I've got the probability that our random variable x1 has no red chips. We have white and then a white. Okay, so that probability is going to be multiplying on the path, 2/4 times 1/3, so 2/12. Okay, so let's come up with a PDF for our x1. I'll do it off here to the side. x1, we'll call it probability mass function because we're in discrete. Okay, so probability mass function for that. So my k value is going to be, looks like I've got 0, 1, or 2 as possibilities for how many red chips I can get out of this first bucket here. Okay, so my k value, and then the probability that x1 is equal to that k value. Okay, what's the probability associated with that? So my first k value is 0. I could have 0 red chips coming out. That only happens here along this path. And that probability is 2/12, okay, which is I'll start simplifying, 1/6 at that point, okay? Now I could have probability that k is equal to 1. Okay, we have 1 red chip coming out. Well, I've got 2 different possibilities, right? I could get a red chip, then a white chip, and a red chip. So I've got these things here, right? So I'm going to sum these up. So 4/12 plus 4/12, this is 8/12. Okay, I can simplify that. Dividing both by 4, I'm going to get 2/3. Okay, that comes from this path plus this path, right? I have 2 different ways of getting there. Okay. Now my last possibility is I could get 2 red chips. Okay, that would happen along this path right here. So that probability of getting equal to 2 is going to be 2/12, which I'll simplify now to be 1/6. So here's our probability mass function for our x1 random variable. That says how many red chips are we getting out of the first bucket. Okay, and it's going to be similar to what we're going to happen with bucket 2, but let's go ahead and add it up because we want to have them in mind so we can create the probability mass function for the sum of x1 and x2. So let's do this again. So I've got a red. This is a 2/4, and then from here I can do another red. The probability that x2 now is equal to 2 is equal to 2/12. So I'm not going to write out all of the math and all the steps like we did before because we have it just up above. And the white, this is 2/4. This is white. And the probability that x2 equals 1 is equal to 4/12. This one goes off to red. And this one goes off to white. So probability that x2 equals 1 is equal to 4/12. Probability that x2 equals 0 is equal to 2/12. It's the same thing. We had the same setup, right? Each bucket, they look identical, right? So that's why our probabilities are the same, okay? But it helps to write out what our probability mass function is for each one of these because I need to have them out so that I can actually put them together to make a probability mass function for their sum. Okay, so I'm going to build up this PDF for x2. Okay, so for our k values, so this is the probability. I'll write it slightly different just so you can see a different way. This is x2 equals k. This notation and this notation are equivalent. Okay, we'll just write them differently just so you can recognize different ways of writing the same thing. So this is 0. It's going to have the same shape as the one up above. 1/6, 1, 2/3, 2, 1/6. And it has the same shape because, oops, sorry, I need to shift that up. because both buckets had the same distribution of red and white balls in there, or chips. Okay. Okay, so that gives us our individual probability mass functions, okay, for x1, which is the number of red chips coming out of bucket 1, and x2, which is the number of red chips coming out of bucket 2. Now we're going to take that. We want to come up with our random variable x, which is the sum of x1 and x2. And we want to come up with a PF for our random variable x, which is the sum of these things here. Okay. So what I'm going to do is I'm going to say, okay, so now we're going to make our PMF for this probability mass function. So I've got my possible k values. Okay, so the k values that I'm going to get. Now I have to think about k is the sum of both. So I need to think about combinations. So I'm going to go 0 plus 0, 0 plus 1, 0 plus 2. So I could have 2 up to from 0 to 2, right? I can have 1 plus 1 plus 2. So I could have 3. I could have a sum of 3, or I could have a sum of 4, right? Because I'm adding up this one and this one, and then this one and this one. Okay, so I'm going to go from 0 to 4 as my possible values for my random variable x. X is the sum of both x1 and x2. Okay, so from here, let's set this up. So my I can go 0. We'll do these in order as we go along. So our probability, this is x is going to equal to k, and that's going to, I'm going to write down, this is the probability of x1 of k, and then probability of x2 equal to k. Okay, and so I'm going to basically look at how I'm building these things up. Okay, so let me make this out into more of a table form. So to have 0, okay, I'm looking at, I'm going to have 0 here and 0 here. This is how I'm going to get one of my options for 0. So this is 1/6 times 1/6. So the only way I'm going to be able to write out some kind of like a sample outcome in terms of our difaces. Okay, so the total sum of these two. This is going to look like if I have 0 on die 1 and 0 on x1, 0 on x2. So this is going to look like 1/6 times 1/6. That's going to be 1 out of 36. Okay, I'm adding these up. Okay, now to get a sum equal to 1, sorry, here we go. To get a sum equal to 1, I can actually sum up 0 and 1, that's a 0, or 1 and 0. Okay, so I'm looking at my k values. I can get 0 and 1, or 1 and 0. These are possibilities for me to actually get a sum, overall sum is going to be equal to 1. So I'm going to go, this is going to be 2/3 times 1/6. This is 0, 1, and then 1/6 times 2/3. Okay, so this is one of them, and that's the other one. Okay, when I put it all together, I'm going to get 2/9, and I'll put a box around it just so we can know that this, I'm doing work inside of our table. Normally your probability mass function is just going to be your k and your probability value, but I'm showing you all the different work, how I'm getting there, and what the possible outcomes are. Okay, so our probability mass functions typically just look like this. Okay, but I want you to see where it looks like, where things are coming from. I find that helpful. Okay, now k is equal to 2. K equal to 2 can happen like this. I can go 0 and 2, 2 and 0, I can go 1 and 1, okay, to sum up to 2. So I'm going to multiply these out and add up each individual piece. So this is going to be 1/6, 1/6 plus 1/6, 1/6 plus 2/3, 2/3. Okay, these are my options for how I was going to get there. When I added everything up, combined all like terms, then I ended up getting, this is just equal to 1/2. That was my probability for when k is equal to 2. K equal to 3, okay, so k equal to 3 can happen if I sum up 1 and 2 and 2 and 1, okay, in terms of my x1 and x2 values. So I'm going to multiply these out and add up these possibles. So 2/3 times 1/6 plus 1/6 times 2/3. Okay, multiply and add find common denominators, and I'm going to get 2/9 as my probability for when our random variable x is going to equal to 3. Okay. And then when our random variable is going to equal to 4, okay, I can get 4 by summing up 2 and 2, okay, x1, x2. This is going to happen with 1/6 times 1/6. And that is equal to 1 out of 36. So now I have a probability mass function, my k values, and my probability values for when my random variable x is going to equal to 0. I have a probability of 1 out of 36. When my random variable x is going to equal 1, I have a 2 out of 9. Random variable x is going to equal to 2. And random variable x is going to equal to 3. Random variable x is going to equal to 4. Okay, so we had to work our way through. I like to put these down because it helps me think about how I can actually get these outcomes and where am I getting the numbers from. It helps me kind of keep things in check. Okay, so let's just do a quick cross check. I'm going to, if I sum up 136 plus 2/9 plus 1/2 plus 2/9 plus 136, all of these things should sum up to 1. Okay, and they do. If you sum them all up, they're going to sum up to 1. That's a good cross check. That kind of helps you know if you've thought about things correctly. If they don't sum up to 1, then maybe you calculated your probabilities wrong. All right, so the next thing that we want to do, let's take this value here, and I'm going to plot it. I'm going to plot that PDF. Plot our probability mass, I'll keep my PDF. So probability that x is equal to k. Okay. So this, I'm taking all those individual values on the PDF, PMF that we've just created. Okay. So I've got a 0, I've got a 1, 2, 3, 4 as possibilities. These are our outcome. This is x is equal to k, right? These are my k values, our possible outcomes. For our random variable x. Okay, and then on our y-axis, these are our probabilities. Our individual probabilities. So we'll go 1, 2, 3, 4, 0.5, 0.375, I did 0.25, 0.125. I found that easier. You can set up your y-axis how you feel like. I found it easier to do it this way. It's up to you. Okay, so now for my 0 value, right, because I could have 0. My 0 value is, I'll put it right about there. I'm going to estimate these because I'm not, this is just an estimated here. For my 1, okay, my 1 value is somewhere like right around here. Okay, for my 2, this was equal to 0.5. This came from our table. For our 3, this was right around here. And our 4 goes back down to about there. I didn't know that. I should have made this out a little bit wider so you can see this isn't drawn to scale, okay, in terms of how wide our boxes are. All these boxes should be evenly width, okay? Now these values, right, these values here that I put on that came from these values here. So when k was equal to 0, I had 136. When k was equal to 1, I had 2/9. This is what I'm plotting, right, on the x-axis and the y-axis. So 2 is equal to 1/2. So I just took our table and I put it into a plot. Okay, so it gave us our probability mass function, or your book may call it a probability density function. Okay, for our discrete random variable, which is the sum of how many red chips we have in bucket 1 and how many red chips we have in bucket 2. Okay, we're going to take this, we're going to take the table that we had before, and we're going to create a cumulative distribution function. Okay, so to actually do that, right, I'm going to say let's plot our cumulative distribution function, okay, our CDF. This is going to go 0, 1, 2, 3, 4. Okay, this is our k value. Okay, what our possible outcomes can be. This is our running total of probabilities. Okay. So you can set up your y-axis how you feel like. This is our outcome. These are our running total, a cumulative sum of probabilities. Okay, so at 0, we start off with 1 out of 36, which is like right about here. I add 1 out of 36 to what I have for 1. So to get my value for 1, I'm going to add 1 out of 36 and 2 out of 9. Okay, so that gives me It's roughly right around here. Oops, sorry. Around there. For 2, I'm going to add 0, 1, and 2 together. And when I do that, I'm like right up around here, right? Because remember, the probability for the sum equal to 2 was equal to 1/2, right? So I'm adding 1/2 to roughly 1/4, which is going to get me almost to the top, where I'm at 3/4 right here. So I'm going to add this 3/4 with the value I got for 3, okay, which was a little bit less than that, a little bit less than 1/4. So I'm right here, just shy of 1, okay? When I get up to 4, I need to be, when I add all these up, we did this, a quick check to see if we're doing things right. I'm going to add up to 4, I'm going to be up at 1. Okay, so I've maxed out. Okay, this is my PDF, my cumulative distribution function, sorry, and then I'm going to just do a quick line through so that you can see it. They should look like what they call sigmoid curves, like this for when we're summing things up. Okay, it's a sigmoid curve, they call it that because it's slightly S-shaped, okay? But it looks like this. Now, depending on, we're going to be studying this later as we go, but depending on how steep this is, right, how steep this mark is or how, you know, shallow this is, that kind of gives us a feeling for what our distribution looks like too, okay? So this is going to tell me, right, like if I want to say the probability that my random variable x is equal to 2 was 1/2. I got that right from my probability distribution function. And if I want to say the probability that my random variable is less than or equal to 2, I need to sum up all of the things that were there before. So this is the probability that x is equal to 2, plus the probability that x is equal to 1, plus the probability that x is equal to 0. It's a running tally, right? It tells me what's less than or equal to that. I'm going to sum that up. That was roughly 27 out of 36. Okay. I could just look on this graph too. The probability that x is less than or equal to 2 is, I go to here and I read it. This says that's the probability that x is less than or equal to 2. Okay. Whereas my probability mass function tells me the probability that x is equal to 2. Okay, so I'm getting 2 different pieces of information out of these 2 different graphs, and they're both valid. We're going to need them both for different things. Okay. So that was working through a whole example from our book. I thought it was a good example. And I think it's similar to examples that you may see in the homework. Okay, and it's something that probably you want to make sure that you're comfortable with doing. You might see stuff like that as you go. Okay, so that's going to be 3.3, right? This is discrete random variables. I'll give you guys a minute to, you know, kind of finish writing things down. I will publish these lecture examples today, right? And then we're going to start 3.4, which is continuous random variables. We usually start with discrete because the math is a little bit easier because we have very discrete values that we're working with. And then continuous random variables, we're talking about like more calculus techniques in order to calculate things. Okay. Right. So that was 3.3. So let's talk about 3.4. Okay, so 3.4, we're dealing with continuous random variables now. Okay, so remember before when we talked about discrete versus continuous. So discrete had, within some interval, I had very specific values for what my random variable could take on. It's going to be 0, 1, 2, 3, or 4, okay, and nothing in between because it was a discrete value. Now with continuous random variables, right, within this interval, my x value can take on any real number of value between the beginning and the end of that interval. Okay, so that's our continuous idea. Okay, so we have an infinite number of possible values that our random variable can take on. Okay, so all right, so let's think about what we need to do. When we did our discrete random variables, right, so it was very specifically, that meant I can look at and say, give me an exact value. When our random variable is equal to this specific value, what's the probability of it equaling that specific value? But now, because it's a continuum of values, okay, I can no longer look at a specific value. I can look at a range of values. So I need to know what's the probability that my random variable is going to take on a value between this one and this one. Now, I could make that range very, very, very narrow and zoom in on the spot that I want to look at. It won't be exact like a discrete because it's a continuous system, but I can make that interval super narrow so I can kind of hone in on what that value might be. Or I can say, let's take a look a little bit broader, okay? But in continuous sets, we're talking about a range of values. So let's write that down. We cannot find probability to one particular outcome, which is our x is equal to very specifically some kind of a k value. But we can do is look at a range of possible values for x. Right, so we're going to say, what's the probability that x is between two values, a and b? Okay, and we have some idea, we have some hypothesis about where x should be, okay? Maybe we're going to zoom in and we're going to see, around this value where we think it might be, with the probability that that might actually occur. Okay, so with continuous random variables, okay, because it's continuous, we're going to call it a probability density function. Now you should know some books, they don't differentiate between discrete and continuous. Discrete gets called density function as well. It really doesn't matter, but just to be a little bit more specific, for the discrete random variables, we called it a mass function. And for the continuous, we call it a density function. But just so you know, they're representing the same thing. And some books just call them all probability density functions. Okay, so sometimes I will abbreviate this as a PDF. Okay, so probability density function, or PMF for probability mass function. Okay, we call this is our function. This is a function of x, right? And it's going to be our probability density function of x. And it's going to describe how the probabilities are spread within the system that we're working with, okay? So if you can think about it, just kind of taking a step back, you know how like McDonald's says they have this quarter pounder hamburger, right? They say all of our hamburgers, I'll write it down. I always think about food close to lunch. Hamburgers are about 0.25 pounds, right? If you buy a quarter pounder, it's going to be about 2.5 pounds. But I'm sure, if I took all of their burgers and I weighed them, right? Or if I took 100 burgers, say in a random sample, and I weighed them, some are going to be 0.24, some are going to be 0.27, some may be 0.2, some may be 0.3. It's going to be kind of a range of values, right? So I'm going to take a look at, right? I can build up some kind of a shape where I expect they're claiming, right, that all of the hamburgers are about 0.25. So if I survey 100 burgers, you don't really survey a burger, but I'll take a random sample of 100 burgers and weigh them. So I'm going to weigh 100 burgers, right? I'll find that, most of them sit around 0.25. This is our probability. And then maybe there are some, that are a little bit less, so 0.24, 0.2, whatever, if I, 0.26, whatever. I'm starting to kind of, as I go farther away from 0.25, right, the probability of finding a hamburger that weighs 0.2 is smaller than finding a hamburger that weighs 0.24, okay? So one of the things that happens is, this is our probability histogram. One of the things that happens is in continuous random variables, and we'll see this in statistics, so 100 hamburgers is actually, it seems like a lot, but it's actually a small number compared to how many hamburgers, say, McDonald's is producing in any given day, right? And so what I want to do is called the law of large numbers. We'll get into it when we get into statistics more. But when we keep sampling larger and larger numbers, right, larger numbers of hamburgers. So let's say the number, page is folded, and the number of hamburgers sampled gets really large. Now, you're going to ask me, like, what does it mean really large? Like, how large is really large? That's actually a great question. And it's something that we're going to talk about when we get into statistics. At what point do we feel confident in our data? And what's the number of samples that we need to have in order to kind of cross over into that place where we feel like the data is actually reflective of the general population. For now, roll with it. We're just going to call it subjectively really large, okay? So again, it gets really large. Then our graph of our probability distribution gets smoother. Right? So instead of looking like boxes like this, we're still looking, so this is 0.25. And then this is, our graph's gonna look like this, okay? And then here, this is our probability distribution, right? It tells us, you know, what probability. So as I get closer to a quarter pound, I have the highest probability of finding the hamburgers that weigh like that. As I get farther away from a quarter pound on either side, the probability drops off, okay? But basically I can say, well, let's take a look. Let's box it in. So 0.2 to 0.3, what's the probability that the hamburger that we sample is within the range, 0.2 pounds to 0.3 pounds, right? So I'm going to take a look. So this shaded area, and actually in reality, the whole area under the curve, the area under the curve is our probability. So actually, I'll write this over here. So area under curve is equal to the probability. Remember in the discrete sense where I said we have all these outcomes, they're all assigned probabilities. If I sum them all up, they should sum up to 1, okay? The same thing is true in the continuous sense. It's harder to see it because a lot of these graphs kind of go off forever in either direction, okay? But what will happen is we'll set boundaries on it initially when we're first starting. Within those boundaries of our definition for our probability density function, the whole area under that curve has to sum to 1, just like all those probabilities in the discrete sense sum to 1. Okay, this shaded area here is going to represent the probability that a random sample of hamburgers, with the hamburgers weigh between our bounds, 0.2 and 0.3 pounds. Okay, so we would actually write this out. This would be, I would write this in math, it would be the probability 0.2 is less than x, which is less than 0.3. Now, quite frankly, it doesn't matter if I include, like if I do the equals, less than or equals at this point, because we're going to be integrating, okay, and these form the bounds of my integration, okay, on my x-axis, okay. So this right here, this shaded region, we call our probability that x is between 0.2 and 0.3, okay, of a pound, we'll call it of a pound, that's our unit. Okay, so the area under the curve represents our probability of our particular outcome. I'm going to specify, based on the questions that I'm asking and the things that I'm looking for, I'm going to specify an interval over which I'm interested and say, what's the probability, right, that what we're looking for is between 0.2 and 0.3. Okay, so that's sort of like a high level view of what's happening, okay? And we'll go into some details on the math before we start rolling into some of the examples, okay? All right, so this is, let me write this down. This is our probability density function. Okay, so that's our probability density function. Tells us how our probability is mapped out within this range here, range of values. All right. All right, so let's think about our cumulative distribution function for a continuous random variable. Okay, so for our discrete random variable, remember we just did this, our discrete random variable, we sum up all those probabilities. We're looking at a particular point, and I'm going to sum up all the probabilities they came up to, and including this point here, I'm accumulating probabilities. We're going to do this again for our cumulative. We write it like this. If little f of x is our probability density function, okay, my cumulative, my CDF, my cumulative distribution function, is capital F of x, okay, which often we will write as being capital F with a big X below. And I'm going to say this is a lowercase x, right? So this is the cumulative distribution function of our random variable x, the probability that it's going to take on a particular value, lowercase x. And what I'm going to do is I'm going to take my PDF and I'm going to integrate over my sample space. F of x dx, okay? When I integrate over my whole sample space, this thing is going to sum up to 1. All the probabilities over a whole sample space will sum up to 1. So let me write that in words. All the probabilities integrated. Integration is a sum, integrated or summed over our whole sample space. It's going to equal to 1. That's just exactly what we showed here. Okay. So now, if I want to be able to say, this is our cumulative distribution function, we're going to actually be talking about techniques for how we create our cumulative distribution function today. And if we spill over, I think we should be able to finish 3.4 today. But if we don't, we'll finish up tomorrow. Okay. So if I integrate over that, I'm going to get this. Now, if I want to think about the probability that x is between two values, a and b, okay, x is my random variable, I'm going to integrate my probability density function over those two values. And it's going to give me the probability. Much like we did with the hamburger example. I had my distribution function, I had 0.2 to 0.3, I integrated between 0.2 and 0.3, whatever that function was, right? And that gave me the probability, right, that my random variable x, which was the weight of the hamburger, was between 0.2 and 0.3. So this is all we're saying, we're generalizing it, I'm sorry, and this is an x, okay? All right, and again, I'll just write it, I'll summarize it here too. So our cumulative distribution function, okay, I would say my f of, we'll call it y, okay, where y takes on some value, is equal to the probability that y is less than or equal to some particular value. Now, it doesn't matter. I'm using a different variable just so you can see we can use whichever variable we feel like assigning. And that means this is y is less than or big Y is less than or equal to a specific value of y. So I'm going to integrate from minus infinity to this little value of y. And I'm going to integrate my probability density function. And I'll call it of a different variable, dt. Okay. Just trying to write it in a different way. This is our cumulative distribution function. This gives us a specific probability, okay? When I integrate my probability density function between two values, it tells me what's the probability between two values. When I integrate it, okay, you know, basically when y is less than or equal to a certain value, okay, I'm taking that and I'm looking at what's my cumulative distribution function of that value y. Because remember, y, our cumulative distribution function says this represents all the values less than or equal to that. So that's what we're doing here to calculate those values. Okay, so I'll give you a second to finish writing that, and then we'll talk about some properties of these before we jump into examples. Okay, all right. Okay, so let's think about some properties. These are theorems in our book. Of continuous probability distribution functions, continuous distribution functions. Okay, so some of these properties that we want to enumerate here. Okay, so the first one that we want to think about is, I'll take these out, I'll talk about them as we're going, and then we'll start incorporating them into examples so you could see what these all mean and how they're being used. So we'll say if our cumulative distribution function, okay, this big F, okay, is typically representing our cumulative distribution function, so our CDF, okay, of a continuous random variable x, okay? So if this big F of x is our continuous distribution function, then if I take the derivative with respect to x of our CDF, okay, I'm going to get my PDF. Right? And we got our cumulative distribution by integrating our PDF. So it stands to reason that if I differentiate my cumulative, I'm going to get my PDF. Okay, so this is little f of x. big F of x. Okay, so they go back and forth there between each other. All right, now our second property says the probability that x is greater than some value s is equal to 1 minus, using my cumulative distribution function. Okay, remember our cumulative distribution function says, right, I'm accumulating all of these values. So when I pick up a spot s, say for example x equals s, that value is all of the probabilities accumulated up until that point. So if I say 1 minus that value, that's going to give me the probabilities of everything above it. Okay, that's what we're saying here. So we're using our cumulative distribution function to help us do this. It's like a shortcut, okay, for us being able to do it. So I don't have to statistics part, just so keep this in mind. All right, so now the probability r is less than x, which is less than or equal to f. Okay, so because we're basically doing, right, we're taking our PDF and we're integrating between different values, it's as though I'm taking my cumulative distribution function and I'm subtracting these values out. Okay, so if I have my cumulative distribution function, I don't need to integrate each time, right? I can actually use my cumulative distribution function and then just subtract these values here. Remember, this is your greater value, this is your lesser value, so make sure that you set up your subtraction right, because our probabilities always should be positive. If you get a negative probability, go back and check your math on things. Our fourth property is the limit as little x goes to infinity of our big cumulative distribution function is equal to 1. Okay, so once I max out, once I reach the top, once I've summed up to 1, I'm continuing at 1 for the rest of time. Okay, so as x goes off to infinity, remember our CDF, it goes up like this. Okay, so as x goes off to infinity, we're already at 1. We're going to stay at 1 forever. Okay, now in the opposite direction, so the limit as x goes to minus infinity, okay, of our cumulative distribution function, this is 0. This is going to, once we bottom out, we're out of our range, our cumulative distribution function, okay, we're at 0, okay. It means that before we've actually started our interval where we're looking at things, okay, we don't have any probabilities to accumulate, which is why we're at 0. We have probabilities, and then we continue at 1 forever. So keep that in mind, because we're going to be drawing our cumulative distribution functions after we calculate them. And you're going to want to have an idea of, before things started, it was 0. After things are all over, right, we're at 1. Okay, I haven't accumulated anything yet. I accumulate a bunch of stuff, probabilities, and I've accumulated everything, and I just stay constant there. Okay. Okay. So let's jump into our examples. Oh, just one more thing I just want to mention too. So if I say probability of A less than or equal to X, less than or equal to B, that's going to equal to the probability of all these different combinations. Right, because remember, on all of these, we're integrating between A and B. Okay, so at this point, it doesn't matter, right, how we're setting up these equal signs, right? So, because I'm going to be integrating the probability between X's between A and B, I'm taking a look at that. I'm going to be integrating those values. Okay, so let's take a look at some examples so you can see how we're actually going to calculate this stuff out. So I've got this PDF. Let's see, sorry, this is example 1. My PDF is 3x squared, and I'm only looking between 0 and 1. My x values are between 0 and 1. So the first thing I'm going to do is I like to graph things out so I can see.
Can you go back for one quick?
I'm sorry, what? Put the notes up from before. Yep. Is that good?
I don't know, because my stream is a little laggy, so like I'm seeing every, like now the thing.
I think the internet, I'm having problems with my internet here. It kind of like cuts in and out, and then my Zoom for some reason is like has been glitching today. I'll give it a minute for you guys to keep writing. You all set?
Okay, yeah.
Okay, great. All right. Example 1 on 3.4. So I've got 3x squared. I'm just going to graph it out just so I can see. I like to look at pictures. So here's 1, here's 1/2, 1, 2, 3. So this is a parabola. It's going to look roughly like this. Okay. So here's our probability density function. Here are our outcomes. Okay. So this, we can think about this as being our x values right here. Okay. So now we want to know, the first question, part A, says, what's the probability that x is between 1/2 and 1? So I'm just going to shade those regions up like this. This is what I'm looking at. So I want to find out what's the area under the curve, okay, between x equals 1/2 and x equals 1. Right, that's all I'm asking here for part A. So part A says probability x is between 1/2 and 1. That means I take my 3x squared, my probabilities. My probabilities are spread out along this interval between 0 and 1 to look like a parabola, 3x squared. So 3x squared dx, and I'm going to integrate between 1/2 and 1. Okay. So when I go to integrate that, right, I use my power rule on this. I get x cubed. Okay, so this would be x cubed over 3, but then I'm multiplying it by 3, so they cancel. 1/2 to 1. This is going to give me 1 minus 1/8, which is 7/8. Okay. So the probability that x is between 1/2 and 1 is 7/8. Right? We've just calculated that out using our probability distribution function. So all of this says here, right, that the probabilities, how they're arranged in this interval here, okay, are arranged in such a way that looks like 3x squared. Okay, so as I progress out along my x outcomes, the probability gets higher, is how we read it, how we think about it kind of intuitively. Okay, so let's think about how we're going to calculate our cumulative distribution function. Okay, so now the cumulative distribution function I need to think about. Remember our cumulative distribution function, right? I had to integrate our f of x, so that gave me x cubed. Okay, so I know, generally speaking, I'm dealing with x cubed. So, okay, so what happens on our cumulative distribution function is this, right? I'll come out with a graph. Okay, I've got this interval of values over which my probability density function is defined, 0 to 1. Okay, so that means that between 0 and 1, I have 0 is less than x, which is less than 1. Okay, that was given to me at the beginning. I'm dealing with the integral of my PDF. Okay, so this is going to look like x cubed, so between 0 and 1, and then it goes up to 1. It's going to look like, you can imagine our cubic function kind of going like this. Okay, x cubed is just our, increasing cubic function. I kind of draw it through it like this. But now what happens is I have to be able to scope out my cumulative distribution function for values of x outside of this range here. Well, outside of this range means x is going to be less than or equal to 0, and x is going to be greater than or equal to 1. Okay, because I want to include all possible values of x, right? So now when x is less than or equal to 0, and I don't have any probabilities to accumulate. So I have 0 values that I've been accumulating. Okay? Once I reach my maximum, right, because I've reached my maximum between 0 and 1 here. Once I reach my maximum, my CDF just stays constant, equal to 1. This cumulative distribution function is going to depend, right, on the nature of the function that you're dealing with. We're going to work through a bunch of different types of problems so that you can see how this CDF and also the PDF, how these values, these probabilities look based on these different curves. Okay, but this is, everything's been accumulated up and by this point here, so it continues at 1. Nothing's been accumulated because we haven't started our interval yet. Here is where our probability density function is being defined. So this is where things are being accumulated as we go. Okay, so this is our CDF. Okay, part C says, what's the probability that x is equal to 1/2? Remember, I already said before that I can't do an exact value, so we're going to show you why we can't do an exact value on here. So this is, I'll just put in here, this is a discrete value. Okay, we're going to see what happens when you do that. So the probability that x is actually equal to 1/2, right? I still need to integrate my 3x squared dx. I need to integrate my probability density function, but I'm looking for an exact value. So I'm going to go from 1/2 to 1/2. You can kind of see where this is going, right? So what that means is I get x cubed, and I'm going to evaluate that from 1/2 to 1/2, which is going to give me 1/8 minus 1/8, which is equal to 0. Okay, this is part C, is sort of a proof of concept when I said I can't give you an exact value. And the reason we can't give you an exact value is because our fundamental theorem of calculus says, you know, when I go to get an exact value out of this curve, we're looking for an area under the curve, okay? So this here is going to give me, there's no area under that curve. It's an infinitely thin slice, okay, at x equals 1/2, which basically is equal to 0 in terms of its area, okay? If I wanted to get an estimate on x being equal to 1/2, I should look at values that are approaching 1/2, really super close to 1/2 on either side, if I want to get like a really close value for what that's going to be, okay? But I'm not there. So that was sort of a proof of concept. Okay, I'll give it a second so you guys can finish writing that down.
Thank you. So the answer for C is just proving that it doesn't work.
That's exactly right. It's, I mean, we don't, I mean, think about like your calculus, right? You're not going to get like a discrete value, because when you take the integral of something, you're looking for an area under that curve, right? If I've got a function, I want to find an area at that curve, I'm just going to look at it. I'm going to say what's, you know, f of x at that particular value, right? But I'm not going to integrate it to get the area under that curve. The probabilities now in continuous distributions, right, with continuous random variables, our probabilities are represented as areas under our probability distribution curve, okay? So if I want an exact value, I have to narrow that window. Think about limits. I have to narrow that window super close to the value that I'm looking for in order to hone in on what that value is approaching, okay? But I'm not going to get an exact value under that curve. Because always, for continuous, it's a range of values that we're looking at. Okay, I'll give you guys a second. And then we'll go on. So I'll move this up here. So in case you're still writing part B and C, you can still see it. Okay, so example 2, we have x, capital X is our continuous random variable, and whose probability density function is given by this, x cubed over 4. And this is being defined between 0 and C. Well, I didn't give you an exact value, right? So what we're looking for is, part A says, what value of C is going to make this density function a valid function? All right, so I need to go back and think about what that means. So when we summed up, we said to make this a valid density function, all of the probabilities under this curve within our range of values have to sum up to be equal to 1. Okay, so that means when I define a range of values for this particular density function, between 0 and 1, between 0 and C, whatever that is, the sum of that area under the curve has to sum to 1. Okay, so that means what I'm going to do is I'm going to set my integral up where I say what values of C is going to make this a valid PDF. The valid PDF is going to be the area under that whole curve within that range of values is going to sum up to 1. So I'm going to say I'm going to go from 0 to C. I don't know what C is yet. That's what we're calculating. X cubed over 4 dx. Okay, and I want that to equal to 1. I'm telling you, it has to be equal to 1. We're going to use this equals to help us solve for the C value, okay? Because the sum of it, all that area has to sum up to 1. So let's go ahead and integrate. So this is going to be x to the 4th, all over 4. The 4 comes from before. Now we're multiplying by 1/4. We're dividing, right, by our new exponent. And I'm going to evaluate this between 0 and C, and that's going to equal to 1. Okay, so I'm looking at, I'm going to get x to the 4th over 16 from 0 to C, and that's going to equal to 1. So what that's going to look like is I'm going to say C to the 4th all over 16 minus 0, right, because I'm going from 0 to C, equals 1. Okay, now I'm just going to solve for C. Multiply both sides by 16, take the 4th root. I'm going to find that C is equal to 2. Okay, so if I go from 0 to 2, given this probability density function, the area under that whole curve is going to be equal to 1, which is going to make it a valid PDF. Okay, so C is going to equal to 2. Part B says, what's our cumulative distribution function, right? Now we know what our valid PDF is. So I'm going to write this down. So our PDF is equal to f of x, which is x cubed over 4, from 0 is less than x, which is less than 2. Okay, so now we know what our valid PDF is, okay? And we want to be able to find what our CDF is, okay, for this part. Now, I need to think, so I'm going to just do a little graph along the side here, okay? I'm going 1, 2. This tells me, this is what we calculated before. This was the C value we just found. This was 0, okay? And we know our CDF is going to sum up to 1, okay? So less than 0, it's going to be 0, and then greater than 2, it's going to be 1. We already know that, right? Because that's our definition. So I've got these values here. So I'm going to say when, I'm running out of space here. So when x is less than or equal to 0, okay, we don't have any probabilities to accumulate yet. We're outside of the range where our PDF is valid. Okay, so we have 0 for our function. Then it's going to be equal to 1 when x is greater than or equal to 2. So we're outside of our range of values where our PDF is valid. We've already accumulated all those probabilities. We just stay at 1 forever, okay? So now the question is, what happens here in the middle? So I've got the range, 0 is less than x, which is less than 2, okay? Well, previously we just integrated to get our cumulative distribution functions. This was x to the 4th over 16. And that's going to describe our cumulative distribution function between 0 and 2. So that's going to look roughly like, in between these ranges, you know, x to the 4th looks kind of like a, got a parabola-ish shape. So it looks like that. It's going to drop roughly out like that, between 0 and 2. Okay, so when x is less than or equal to 0, we haven't had any probabilities to accumulate, so it's 0. Between 0 and 2, our range of values for our PDF. We have our cumulative distribution function. That's, we integrated our PDF to get that. Then beyond 2, when x is greater than 2, we've accumulated everything we're going to accumulate, and now we're just stuck at 1 forever. So this is our cumulative distribution function written out, and this is it graphed, okay? You want to have both. So the graph is going to help you conceptualize what it is you're trying to do, and then this is the actual function that's being defined here. Give you guys a chance to write that.
Is the graph part necessary for the answer for B, or is the piecewise function?
The function for your CDF is actually the answer. Personally, I like the graph. It helps me conceptualize it. Unless you're asked to graph it, you know, don't sweat it. I like to do it because it helps me think about like what's happening and where I need to put things, and especially when I'm thinking about my boundaries, you know, and then where things are changing. We're going to do a piecewise PDF in a couple of minutes, so you'll see how it can get complicated. But the graph is not necessary. This part here is your answer, the actual function itself.
Okay, thank you.
Yep. Unless you're told specifically to graph it, in which case you should. Okay. I will publish these online today so you guys can see them. Okay. So let's go to example 3. There we go. Example 3 says, we've got this function, f of x is a probability density function. Okay, it's a piecewise function here of a continuous random variable x. We want to find and graph our CDF, our big f of x. Okay, so given this, so let's see how we can do this. So I've got two functions here, right? I've got one of them, I'll just write it down here. So one of them is x plus 1, and that's when x is between -1 and 0. And then we have another one, x is equal to 1 minus x, when x is between 0 and 1. Okay, so like I say, I like to graph things out. So I want to be able to think about what's going on. So I'm going to graph the -1, +1, and 1. Okay, and then here's 0. So if I were to plot this out, right, x plus 1, this is a right, it's a positive slope and it has a y-intercept of 1. It's going to look like this, right? And it's going to go on like that, and it's going to go negative, just as a function. we're defining it between -1 and 0. So really, I'm just looking at these and these points right here. Okay. This graph right here, 1 minus x, is the y-intercept of 1, has a negative slope, so it's going to look something like this. You know, this as a function would go on in both directions. We're defining it between 0 and 1. Okay. This is to make it a valid PDF, right? So valid PDF is going to make it 0 otherwise. Okay, we're just going to assume it's 0 otherwise. Okay. All right, so now we have just kind of a visual representation of what's going on. So when I want to think about my cumulative distribution function, I have to think about 4 different intervals, right? Okay, so my 4 intervals are going to be, the first one is when x is less than, we'll say less than or equal to, because it's not included, -1. So what happens here, right? When x is less than, this is my x-axis right here. When x is less than -1, okay, that's my first interval. My second interval is what's happening here. So between -1 and 1, oh, sorry, -1 and 0, my bad, -1 and 0. That gives us this range here that we need to be taking a look at, that part of the function. My third interval is looking at this bit. So I'm going to go from x is between 0 and 1. I'll include 0 in this one. And then this bit here, when x is greater than or equal to 1. So I've got 4 intervals because I need to include all 4 of these in my, excuse me, in my cumulative distribution function. So looking at it, just we can knock off a couple of these as we go. So as we look at this, right, we know before we've even started our interval of analysis, right, so when x is less than -1, we know our cumulative distribution function is going to be 0. Right here, we haven't even started. We have no probabilities to accrue yet. Likewise, right, when we go x is greater than 1, we've accumulated everything so far. So we've already maxed out at that point. Okay, so we just need to come up with an analysis for this region and this region to think about how we're going to take a look at our cumulative distribution function. Okay, so let's talk about interval number 2 first, which is between -1 and 0. Okay, so I want to come up with a cumulative distribution for that part. So I'm going to think about my big f of x, my cumulative, right? And I'm going to go from -1 to x, right? And I'm saying -1 to x because I'm looking for a function. I don't want a value. I don't want the area under this curve. I want a value. I want a function that's going to describe that. So I'm going to translate, this is going to be t plus 1 dt. All I did was change the variables around so that I can integrate and get this as a function of x. So when I do this, right, I'm going to get 1/2 t squared plus t, and I'm going to evaluate that from -1 to x. Using my fundamental theorem of calculus, okay, what I'm going to get out of here is 1/2 x squared plus x plus 1/2. Okay, let's just take a reality check, right, and think about that one for a minute. So how much probability has accumulated when x is equal to 0? So right here, how much probability have we accumulated when x is equal to 0? Well, I can take my cumulative distribution function that we've just figured out, right, this one right here, and I can say 1/2 0 squared plus 0 plus 1/2. So I've accumulated half of my probability by 0 by the time I reached x equals 0, right? And that makes sense. Okay, so let's just write this down in words. We have accumulated by x equals 0. Okay, that's what this is telling us in math, in words, just so we can conceptualize it. So by x equals 0, I've got half of the probability total. Now I need that because I need to actually include that half when I think about my second interval. So my second interval, right, I'm going to go from 0 to 1, okay? And I need to build up, I have to use a different function, but I also have to take into account that when x is equal to 0, I have half the probability that, that I would have started with. So f of x is equal to 1/2. This is how much we've accumulated so far, 1/2. Plus, now I need to integrate from 0 to x. I'm looking for a function. And so along this pathway, I'm looking at 1 minus t dt. Okay, so when I integrate this, I'm going to get the 1/2 from before, plus this is going to give me t minus 1/2 t squared, and I'm going to evaluate this bit here from 0 to x, okay, which is going to give me 1/2 plus x minus 1/2 x squared, using my fundamental theorem of calculus. Okay, because think about it, this describes the second half. I have to take into account how much I've accumulated already when I start my interval, and then find out the rest of it that I'm going to be accumulating as I go. Okay, and you can think about it, if we were to say when I go f of 1, right, I should have accumulated everything. So if I plug in f of 1, I'm going to get 1/2 plus 1 minus 1/2 1 squared, right? 1/2 minus 1/2 plus 1 is going to give me 1. Okay, so by the end of this interval, I will have accumulated all the probability that I'm going to accumulate, accumulated 1. So these are good cross checks. I needed to do this one because this interval here, x equals 0, I need to include here, okay, when I calculate the next portion of my CDF. So let's put it all together. So my total CDF, my cumulative distribution function looks like this. F of x equals, right, it's a piecewise function. Okay, oops, sorry, I'll put it all together. So it's going to be 0 when x is less than or equal to minus 1. Okay, it's going to be 1/2 x squared plus x plus 1/2 when x is between minus 1 and 0, as we found in that first interval. Then it's going to be this 1/2 plus x minus 1/2 x squared when x is between 0 and 1. And it's going to be 1 when x is greater than or equal to 1. So this is our cumulative distribution function right here, our piecewise function. And if you wanted to see the graph, I'll just do a quick graph right here so you can see -1, +1, here's a 1. So I've got a 0, this is my f of x, my x. So it's a 0 here, and it kind of goes, this is like a parabola-ish. It's an upward facing parabola, it kind of goes, this is 1/2 like this. And then to here, it goes off to 1. And then I've got a kind of a downward facing parabola like that. Okay, it's a generalized graph. I'm kind of sketching it. Okay, this is your answer right here. This can just kind of help you conceptualize, unless you're asked specifically to plot it out. Okay. I actually have one more example to do. I'll let you guys tell me what you think. I can do that one example tomorrow, one more example tomorrow. It's another piecewise function for our PDF, okay? And coming up with our cumulative distribution function, and then also looking at different probability values. How do we sum up those? I can do that example right now and then put everything up online, or I can finish the example tomorrow. Do you guys want to tell me, do you want me to spend like the next 10 minutes doing the example, or do you want to just see it tomorrow? It's up to you. I'll look in the chat. You can think about it and tell me.
I think doing it tomorrow would be good.
I'm sorry, can you say that louder?
I think doing it tomorrow would be good.
You want to see it tomorrow? Okay. Anybody else? You can write in the chats if you want. Do you want to see it tomorrow, or do you want to see the last example right now? That works fine. Tomorrow. We're getting an even spread. Tomorrow. Looks like I'm getting more tomorrows than right now. I'm getting a lot more tomorrows than right now. Okay, so I'll let you guys sift. This is a lot of material to process. I'll let you guys sift through it, and then we'll finish up 3.4 tomorrow with this one last example. If you want, come to tomorrow's class with questions. You can ask me after we finish 3.4. You can ask me questions about the homeworks. You can ask me about the test reviews. You can kind of think about it as a review session for an exam. We will have our exam tomorrow. The homework tomorrow will be due by midnight again, and then I'll start posting homework solutions. I know I'm posting them, basically before they're due, but hopefully you've kept up with it, so you can just check your answers, so you can see if you're doing things right. And then I'll open up the exam like I did last time at 4 p.m. tomorrow, and then it'll be available until Friday at 4 p.m. as well. Now, that means that you can't see it until you start it, but once you start it, essentially 100 minutes, which is our class length, 100 minutes plus 15 minutes to upload. Okay, so 100 minutes to take the tests and 15 to upload, okay? Unless you have accommodations, in which case we've already talked offline on how we're gonna accommodate that. Anyway, I guess I'll see you guys tomorrow. Have a great day. I'll also have office hours today if you guys have any questions. Okay?
For the test,
yeah.
How many questions are likely to?
I can take a look at previous tests. It's you definitely being able to do it within the time frame and maybe even having some time left over to check your answers. And again, we're assuming that it's not meant to like trip you up, but it should be as hard as like the review sheet, as hard as like the homework problems that you've been doing. And it is open book, open notes. You can't talk to each other. You can't talk to another person. You can't look at from or other kind of solution solvers. As you know, I need to see all the work out, all the work that you're doing. So even if you have an answer, I need to see everything in order to get full credit. Yeah, but don't go into it thinking because it's open book, open notes, you don't really have to study. Pretend as though you were taking it in class, right, without any kind of access to resources. And then that way you only need your notes in case you've gotten a formula or you just can't quite remember what is that thing supposed to be, but you're basically just kind of taking it, okay? Okay.
So would that include if we had like a NPK, if our calculator can do that, we still write it out?
Yeah, so you'll want to set it up, and then you can do it on your calculator if you want to, but don't just write NPK, like just set it up so I can see that you understand what's behind it all. I mean, like, this is a class for engineers, so the goal is for you to understand the background on things, not just that you can plug it into your calculator, but you can certainly use your calculator to do the calculations, but just show me that you know what things are and how you're setting it up. Does that make sense?
Yeah, thank you.
Sure. Hey guys, I'll see you later. Have a great day.
Thanks.
Bye-bye.